Okay, so we have a kid flying a kite, and they say that her hand stays at a constant height, and the kite also stays at a constant height. And from 1.6 up to 16.6 is a difference of 15 meters. So this kite is absolutely always 15 meters above her hand, but it's getting blown out horizontally. So it starts out, the kite's over here someplace, and then some time passes, and the kite after that is still 15 meters up, but it's a little further over. And then some more time passes, and the kite is still 15 meters up, but it's even further over. And so we get that kind of progression where the kite is moving further and further to the right, but it's not moving vertically at all. Notice the right triangles? Glad to see those. There's always a right triangle here, and if we call this distance h, we've been using y a lot, so let's get away from that. And the horizontal distance is x. We should be able to set something up with that. What they're asking about is the length of string, as in the hypotenuse, and how much it's increasing when the kite is over here and there's 30 meters of string out. So for the hypotenuse, I'm going to use S for string. And the Pythagorean theorem tells us that we can say x squared plus x squared equals s squared. And if we differentiate that, 2h dh plus 2x dx equals 2s ds. And as usual, I'm going to divide the whole works by 2 just to get those out of there. Okay, divide by dt, and we got a rate equation. And then we'll see how much of it we can fill in. Okay, height. Well, the height here is 15 meters. dh dt, now this is funny. How fast is the height changing? It's not. It's not changing at all, which means that whole term's going to drop out. This happened because up here, and I didn't do this on purpose, this was an honest lapse, I forgot to put in that this is 15. What I should have done is say that the height is 15, 15 squared is 225. If I had put that in here, then I would have taken its derivative and gotten 0 instantly. I forgot to do that, but the formula gave me another chance. It said, okay, tell me the height and tell me how fast the height is changing. And at that point, I remembered, oh, wait, the height is locked in. It's always 15. And so the math is saying, okay, in that case, I'm going to make this whole term 0. So in this case, I get away with not remembering that the height is a fixed value. This is going to be 0 anyway. So thanks, math, for having my back there. X, here's a problem. We don't know x. We're going to have to find that. I'll leave a space for it for now, and we'll do our side calculation in just a moment. dx dt is how fast x is increasing. They tell us the kite's getting blown out 4 meters per second, so dx dt is a positive 4. S, the string length, they tell us is exactly 30. And ds dt is the thing we're trying to find. So the only thing holding us back really is the value of this x, the horizontal position, which we should be able to get with, you guessed it, a side calculation. We have our formula here, h squared plus x squared equals s squared. Plugging in what we know here, the height is 15, always. X, not sure. But we're told the string length is 30 at our moment of interest, so let's see what we can do with that. 15 squared is 225, plus x, don't know. 30 squared is 900. X squared is 900, take away 225, which is 675. And the square root of 675, it's going to be just under 24, I think. Oops. Wrong, it's just under 26. 25.98. 25.98 is our horizontal position. That's x. That goes down here. This is our x dx dt term. So 25.98 goes there. So to solve for dSdt, I have to do my entire left-hand side and divide by 30. Now, because this term vanishes, my whole entire left-hand side is not as impressive as I make it sound. 2598 times 4 divided by 30 gives me that dSdt is 3.46 meters per second. It's positive, which means the string length is increasing, which makes sense. This distance can only go up. And that should be our value.